Hello everyone, and welcome back to a new episode of SHENZHEN I. Before we get started on the next puzzle, I wanted to revisit the one that we did last episode. This one, right? Virtual reality buzzer. We did poorly on, we did okay here, but not well. Wait, is this the one that I'm thinking of? I think it is. Yeah. Oh, no. That's not the last one we did. The last one we did is further down here. I assumed it had scrolled down more. But no, this one. We did quite poorly on production cost and quite poorly on power usage. And let's just review this this design briefly. So remember, the idea was that this thing is going to, it's a wireless thing, so it can send multiple things per time unit if it wants. And so some time units it sends us nothing, other time units it sends us a color and the length of time. And so we had this guy decode the whole thing, send 3 different color values along this XBus, this shared XBus, to the 3 controllers for the 3 different colors. And then it sent them like a time thing saying how long to keep it, and they set the color output accordingly. And this was the only way that I could really think of to do this. But when I was done with that episode, I said, okay, now that I've solved the problem, let's go watch the Scott Manley video where he solves it and see what I missed. Because although in some ways this is sort of an ingenious solution to, I don't know, a very complicated approach to the problem. You know, we actually managed to wire this all up and use 2 different XBuses and sharing. We did some cool stuff, but it doesn't really seem like it could possibly be the best solution, right? And indeed, Scott Manley's solution is way better, and so I want to re-implement his same algorithm, compare and contrast. Well, really just contrast. There's not a lot of comparing to be done. I guess it's not quite fair. There's a bit of comparing. I have a new phone. Let me figure out how to put that on vibrate before it starts making noise. There we go. Ha! I remembered before it made noise, unlike in the past. So yeah, as I said, his contrast and see if I can generalize why my solution is bad. Like, okay, it's bad because I used too many chips, but that doesn't tell me anything actionable, right? What I want to do is see if I can find a pattern that this problem I ran into might be a general case of compared to his solution. So, okay, I'm going to save this one, not edit this design, but we're going to go back and start a new design. And so the idea is, well, let's actually not do that just yet. Let's grab this guy. And so, look at, I think a lot of what's going on can be explained starting from incorrect assumptions, or perhaps failing to update assumptions when things change. So I had each of these guys, I created 3 different pins because I knew I was going to need 3 registers, as I said in the last episode, to store the color data in, right? 1 for each color. And then each cycle I was going to output the current color condition on the pin, so I needed 3 registers to control colors. Fine. But if you look, we're not actually doing that, right? Every clock cycle, we write into our accumulator, the only register we have, a value which might be a color or might be 999, and then we just use it for the current cycle and throw it away. So this is a case of not updating my design when my assumptions or my constraints change, right? I had in my head at the beginning this idea that I was going to need 3 registers, and then I later realized, as I was struggling to fit everything onto the chip, that, oh, I don't need to use a register for this. I can just write to the port once, and then leave it alone. And that frees up the register to do other stuff. Well, great, but now that I don't need a register, I don't even really need all these chips to be separate anymore. Now, just from that alone, it's maybe not so clear how we can even, like, okay, there's a lot of work going on in each of these guys. Could we even really combine two of them into one? Maybe not. But there's even more that we can improve once we realize that we don't need a register here. And so the second realization is another instance of not updating my design when my assumption changed, but also another thing that I think is a pattern that I've noticed in the ways that I make my solutions badly, which is that my I/O devices tend to be too smart. They're doing too much. All this entire chip is really doing is like handling the values, taking the stuff that it gets over XBus somehow and writing them occasionally to this pin, to this wire here, right? And I've made that quite a complicated job, haven't I? It has to read from XBus every cycle, and then it has to decide some stuff about what it read, and then it has to read from XBus again, and then it has to decide about what it's read, what to do. Whereas in the solution that I'll show you shortly, there's a lot of S's in that sentence, you can actually design for extremely dumb I/O controllers here that just do nothing except take a number off XBus, write it to a pin. Take a number off XBus, write it to a pin. So this is, in a way, what's happening in Scott's solution is he's put all the brains of the entire thing into this one chip, which means that all these other devices that are doing kind of intelligent things, in the sense that they're like making decisions, can be thrown away, and they can be simplified down to just handling I/O, so that we have one chip doing all the real work, and it's just like, oh, it doesn't have enough I/O ports, so we'll write to XBus and have XBus use one of these chips to basically just extend the number of I/O ports available to this guy. So I think that, like, I'm used to having the components that I write be a little bit smarter than necessary. I don't know if this is indicative of like a software versus a hardware background, but I'm like, what's the dumbest thing you could possibly do? Well, you receive a message, you look at it, you decide what to do, and then you do a thing. But in this game, and maybe in real hardware dev, who knows, you can be dumber than that, right? You can just get an input and do a thing. Don't look at it, don't decide what to do, just do the dumbest thing you can imagine. Okay, so all that exposition out of the way, let's go re-implement this now. So we're going to take this guy here, and I'll move it up a bit just because I think it looks nicer. And what is this? Note? Note? I've never seen a note before. I guess we unlocked that because... Oh, geez, and we got these guys too. Oh, are these finally and and OR gates and stuff? Yeah! Alright, we got AND, we got OR, and I think that's XOR? Interesting that they have two outputs. I don't know what those are about. Maybe it just drives... They're probably like... Oh, let's look. Are these XBus or simple I/O? I don't know. We'll figure it out later. We'll read the part spec, but we certainly don't need them for this this little adventure here. What is this? Wow, it's got so many numbers on it. Amazing. And this is a NOT gate. Incredible. Okay, well, we discovered a bunch of exciting stuff, but we're not using any of it right now. Okay, so here's the idea. We're just going to take the input from this, feed it here, and we're going to take is it this guy? Yeah, this is the small one with two I/O ports. Can I put wires there? I can't. Okay. Do I need to put wires there? Oh, I don't. All right. Ah, come back. And we'll wire this guy's X input to here. And we'll have this guy be in charge, I suppose, of green and blue. And we'll leave this guy in charge of red. Okay, great. So it turns out that all we really need to do is basically the same control loop we were doing in here in the previous exercise, or the previous solution to this problem. But instead of sending out color values every cycle, we just only send them out when there's a need to change colors. And otherwise, we just don't send anything and nothing happens. Right, so this is perhaps another way that my assumptions, my incorrect assumptions led me to make a poor design, was that I assumed that each of these sort of edge devices, the ones that I had in charge of managing color, needed to do something every cycle. And that assumption led me to say, okay, I need a clock to control all of them, and they need to like manage their data and so on. But they don't. If there's no need to change the color outputs, then I don't need this guy to do anything. So in fact, let us first start by writing this guy, and slits on x0, please. I'll just move x0 to p0 and move x0 to p1, and that's the entirety of his programming. He does nothing but this. Wait until there's an input, and if there is, that must mean it's time to change colors, so we'll read in our two colors and write them. Yeah, and P0 is G, and P1 is B. So this is correct. Great. So much simpler than what I was using 2 chips to do. We can do in 1 chip with like no work at all. So this is a big improvement, and the reason I'm talking through this all so much is because I really want to, I mean, it helps me think through what it is that's going wrong when I come up with poor solutions to talk it out. And I want to make sure that you guys are participating in that, or at least, soaking it in, You're not very active participants in this conversation, if I have to be honest. You occasionally send in a comment, but most of the time you guys sit there and chill, and that's fine. Anyway, and so I want to make sure that I'm noticing and expressing the reasons behind, sort of the root cause causing the symptoms of my stupid, crappy designs. Okay, so enough fluff. Let's see what's going on here. So first we're going to do basically what we did before. Move x0 into, and I think we were using dat for this because we need act to do math on. Great. Move. And then we're going to test if it's equal to minus 999. Test equal dat of minus 999. And if it is, we're going to want to skip a whole bunch of instructions. And I'm not sure yet whether we need a jump or if we can just make them all conditional. I think we can make them all conditional. So let's try it. If it's not minus 999, we need to actually do something. So we'll use a minus here. We'll move dat, which is the first color, red, onto our simple I/O pin, P1. And then we'll just move stuff from the input, x0, onto the dumb chip down here on x2 twice. Make these minuses. Now we've communicated the colors, and we just need to move x0 into ACK, which is our timer. And at this point, I think, we can just leave the negative instruction mode. We don't never needed to do any jumps or anything. And we can just go back to unconditionally executing a decrement of our counter. So let's sub 1. Hang on. Before we sub 1, we need to check. Do we need to check whether our timer is 0 before or after we subtract? We need to check before we subtract, because a 0 length pulse, if we should get one, should result in never sending a color. And a 1 length pulse should result in sending a 1 length color, which means we have to check before we subtract. Okay, so first, we're just going to test equal ACK of 0. And if it is, then we will write 0 to all the interesting places. So if some nut job sends us a 0 length packet, we'll briefly flicker a light on, but it'll happen in the blink of an eye and no one will know the difference. So we'll just, if it was 0, we'll move a 0 to P1 and move a 0 to X2 twice. Excuse me. And then we will unconditionally decrement sub 1. Now, at first when I was thinking about this problem, I was thinking, we can save an instruction by conditionally decrementing. We don't need to decrement if we're already at 0, right? Well, wrong. That would lead to correct behavior, but it would actually cost us more power, not less. Because we would not do the subtraction in this cycle. That would be nice. But then in the next cycle, our timer would still be 0, and we'd do these 3 extraneous moves again. So it's better to let timer roll over down to -1 and keep subtracting from it, spending 1 power every cycle, than it is to not do the subtraction and have to do these 3 writes every cycle. And these 2 writes are super, super expensive because they cost 1 power here and like at least 1 power here. So these 2 moves are costing us 1, 2, 3, 4, 5 instructions, 5 power. So they're like super expensive. But I think this is done, right? We're just gonna sub 1 and then roll over back to the top. Let's see what happens. So we tested if it's 99, it is. We tested the ACK is 0. It is. Okay, fine. So we're sending a bunch of zeros, which I guess is fine. We're explicitly initializing the state of our thing and rather than letting it by default be 0. Now we test if the thing was -999, and it was. Was our accumulator 0? No, it was -1, so do nothing. Well, subtract 1. Now we read again, and it's still -999. Oh, we never slept. Ha ha ha. Sleepwalk. There we go. Okay, let's skip over that again. Great, now time has actually advanced. Very good. And we're about to read these values, so some actual colors arriving. Dat wasn't -999, so we move dat, which is 0, onto P1. And we copy our 50 and ship it over to that controller chip. And it just bloop, copies it straight to the green output. And then we do the same thing again, and it copies onto the blue output. And all of our stuff is going great. We get a new thing, and we just write out all the colors it had in the same boring way we've been doing. Let's make sure that we time out appropriately here. Is the accumulator 0? Yes. So we write zeros to everything and turn off the light. Great. So, I can speed it up, that's right. So overall, a much, much, much simpler solution to the same problem that exemplifies a lot of the ways that I was, and still probably am, doing things wrong. And I hope that we can take the lessons from this better solution and try to apply them to more problems in the future. So these numbers all look more reasonable. So I'm starting to come to the conclusion that this is actually what it was supposed to be, i.e. a graph of all the players' solutions. What was confusing me was that it was saying here, oh, hey, Malloy, like, this is just you, it looked like. And so I was not really sure what was going on. I feel like it would be less confusing if it didn't use my Steam name here, because making this list a list of one implies that there's only one name's worth of thing, one username's worth of data in this graph. And since there are no other Steam friends for me to compare to, putting my name on the list doesn't make it any clearer. Whereas if it just said you, 8 yen, I'd be like, oh, okay, that's what I have, 8. And here's the graph of what everyone else had. By putting my name here, they're sort of implying to me some kind of weird things, I feel like. Maybe I'm just dumb, but that's my user experience feedback. So how are we doing for time? That probably took like 15, 20 minutes? 20 minutes, yeah. All right. So once again, as you guys can see, I was not professional enough to set up a real timer. I keep forgetting, and the other games that I share with a full screen, that I record a full screen on, are sort of easier enough to split up into bite-sized chunks that it doesn't matter that I'm not really explicitly tracking time. At any rate, I think 20 minutes is fine for this episode, even though you just saw the same puzzle again. But hopefully, seeing it from a new perspective was as revealing to you as it was to me. And in the next episode, we will actually move on to the next puzzle. Thanks for watching, and I'll see you next time.